Welcome. This morning, I would like to talk about the newest funded CROSS project, my own project, which is titled the Open Source Autonomous Vehicle Controller. A little bit about me. I am a third-year PhD student in computer science and engineering. My focus so far has been primarily on control theory and embedded systems. And prior to graduate school, I was a principal member of the technical staff at Applied Materials Incorporated. My advisor is Professor Gabriel Elkheim. Of course, he is the director of the Autonomous Systems Lab at UC Santa Cruz. He's a recognized expert in the field of embedded systems and mechatronics. And of interest here is under the tutelage of him and through his lab, the Slugs autopilot, which was an early open source UAV autopilot, was developed. To a great extent, my work here will build upon the success of that project. So by way of background, autonomous vehicle control is obviously a very active research field. You can see in the images above 3 different types of very, very different vehicles, from the UC Berkeley legged robot on the upper right to an autonomous vehicle in the middle picture to a novel water-going quadcopter that's being developed down in Monterey. They exist, of course, in pretty much every environment, both terrestrial and extraterrestrial, if you want to consider spacecraft as well as the Mars rover, for example. One thing that all of these vehicles have in common, however, is that they all utilize a real-time embedded controller. That is to say, they have a controller which takes in sensor data, estimates the state of the vehicle, and based on that state estimate provides some action that it takes in the world, whether it to change its direction, to increase its speed, to move its limb, whatever. They all have some form of real-time control. In addition, most of these applications, at least certainly the ones that are under development today, they also have a much higher level of control and interaction. And they use multiple computers for this. For example, they might have a computing module that performs some sort of optimal guidance control or navigation. They might have a computer that's dedicated to measuring and interpreting the world through computer vision, or they might have a LiDAR measurement. They might have some non-real-time needs for communication to a ground station or to other vehicles. But what is essential in all of these is that there is no common real-time platform for research and development of autonomous vehicles. That is to say, each one of these projects has developed its own real-time controller based on its applications. And that's what we want to try and change with this project. So the proposal, therefore, is that we want to develop an open source, real-time embedded controller for autonomous vehicle research and development. And in particular, we want this controller to be vehicle agnostic. That is to say, we want it to be useful for a larger number of vehicles than just a single class of vehicle, like an automobile or a quadcopter, but one that can be applicable to almost any real-time autonomous vehicle. And equally important, this controller will automate that data pipeline that will allow seamless integration to a single or multiple external processors that will enable those computationally expensive operations that I just discussed, such as computer vision, guidance, navigation, model predictive control, you name it. We have several objectives for this project, starting with simply defining specifications for this vehicle agnostic vehicle controller. We will develop an embedded hardware architecture and a corresponding modular firmware based on that hardware, both of which will use embedded programming and embedded hardware best practices. To demonstrate its value, we need to implement it on some vehicle ourselves, and so we plan to implement it onto a scaled automotive platform. We also intend to demonstrate the advantage of having that higher level control performing some more advanced computation. So we will demonstrate optimal control with obstacle avoidance or something like that on the vehicle. And then, of course, we need to publish our results for both the controller design, both hardware and firmware, and we want to publish the results of the actual vehicle testing results once we've completed that testing. I want to give you a quick overview of what the firmware architecture looks like. This is a block diagram demonstrating how we intend the data flow to occur within our controller. Everything within the grayed out box is what we intend to produce. That is the firmware that will allow communication to the supervisory controller or controllers up above, as well as to take input from a manual control down below. But fundamentally, the architecture is intentionally quite straightforward. It will take in real-time sensor data from the world. From that sensor data, it will provide an estimate of the state of the vehicle relative to the world. That is to say, its velocity, its position, its attitude, its pose, what have you. From that optimal state, then the controller will make some decision based on some guidance from a supervisory control on where it wants to go or what it wants to do in the world. And that controller will then provide the necessary commands to the outputs of the vehicle itself. These are typically going to be motor commands or servo commands, but they could also be digital outputs of various forms as well. The blocks in green are essentially modules within the firmware that are easily replaceable by the adopter of the architecture. In other words, if you are a vehicle controller and you want to provide your own custom state estimation algorithm, this architecture allows you to develop it and drop it in as a module into the firmware, simply by replacing a single file or a single couple of files. If you include the header. Similarly, if you want to have some, if you want to develop your own real-time control algorithm for the vehicle, in the same way, all you do is you simply replace a C file and its associated header. And thus, we think that we can offer an advantage over a more sophisticated but yet more limited approach that, for example, exists for UAVs today. From the hardware side, we have this block diagram. Again, everything within the main gray box is what we intend to produce as part of this project. In its simplest form, it's a microcontroller and an internal sensor, an IMU, which estimates it measures its state relative to gyroscopic forces as well as inertial forces. And in this case, it will also have a measurement of the magnetic field. So it basically is a so-called 9 degree of freedom measurement unit that estimates its state relative to those. Additionally, however, of course, it will take external sensors, and we will define several of them utilizing the most commonly used interface protocols for sensors, mostly digital sensors these days. For example, a vehicle might require a GPS unit. It might have a need to know its altitude, so it might have a barometer. It might be measuring the motor speed or the joint angle of an actuator. And so it might need an encoder measurement. And so we'll provide examples for many common interfaces and many common devices. And then the microcontroller will also provide a variety of outputs, the most common of which would be a PWM signal or a digital signal. But there might be some user-specified outputs that they can provide as well. And there will be plenty of connectivity to allow that sort of output. And then it will inherently provide a connection via some form of high-speed serial to a higher level processor or multiple processors. Additionally, it'll have a dedicated channel that can communicate via radio to a ground control station such that it can mimic the usability that is done for UAVs, for example. And then it'll have a manual remote control input as well for a human user to take over control at any point. To ensure that this technology is employed as widely as possible, we want to provide, not only do we want to take advantage of the robotics open source ecosystem, but we actually want to provide links such that other people can, using these open source applications, will be able to immediately apply them to our system. And in particular, there's two robotics foundations that seem to be the most widely adopted today. One is called the Dronecode Foundation, primarily formed around UAV operation. But there's two applications in their portfolio that we intend to use and implement on our controller. One is a lightweight protocol, extensible protocol known as MAVLength. In fact, Slugs was one of the early, the Slugs autopilot developed in Gabe's lab was one of the early influencers of that particular communication protocol. Dronecode also produces an open source ground control system called Q Ground Control that speaks to its autonomous vehicles via MAVLength, and we intend to use both of those things in our project. And then finally, or in addition, there is the Open Robotics Foundation, which has two main applications. One is called the Robot Operating System, or ROS, which allows your component to be integrated into a larger ecosystem of robots. So our controller will inherently be integratable to ROS, primarily actually through a link called MAVROS, which is a decoder that changes a MAVLength communication protocol into a ROS node. Additionally, Open Robotics has a very widely used and very capable simulator known as Gazebo, and we will be using that during the development phase. And then finally, of course, any kind of computer vision these days is done using open source software, primarily using OpenCV. So to the extent that we implement computer vision on our system, it will be on a computer running OpenCV. To provide sort of an existence proof of our approach, I found this paper from ETH Zurich, published in 2018, of an autonomous race car. That's pictured in the image in the upper center. More of interest relative to our proposal here is that it actually has three separate modular computing systems. One which is dedicated to computer vision, shown in the left-hand block of the block diagram. Then they have the so-called master computer, which is doing their mapping and their LiDAR data, as well as their sensor fusion, all in a separate computer. And then they have the real-time computer known as the ECU in this case, which is doing the real-time control based on the guidance from the master computer. And to be clear, what we're proposing is the real-time component of a system such as this. And the only major difference here with our proposal is we're both using a distributed architecture, but with our proposal, all of the real-time sensor data, in order to really enable best practices real-time control, will be coming in through the real-time computer. The exception for that might be the LiDAR, or more likely the camera might be implemented separately from the real-time computer, but almost all of the other sensors should come in into the real-time computer. These are what we've defined to be the vehicle requirements for our test vehicle. Like I mentioned earlier, we want to choose an automotive platform. And so something like the image on the right, where we have a scaled electric car, rear-wheel drive electric car. The sensors required to operate this vehicle will be the motor velocity, or velocities in the case of a dual motor car, the steering angle itself, as well as some localization technologies. A GPS will almost certainly be implemented. The IMU, which I discussed, will be part of the project, so it inherently is there. And then the potential for LiDAR or machine vision will be integrated for the higher level control that we discussed earlier. So that's it for the main proposal. Of course, I have more data regarding milestones and objectives and things of that nature, but I really wanted just to give you a sense of what our project is and what it entails. And with that, I would like to open up the floor for questions. Thank you very much.